So let's now try another example and try to determine the rate law for this particular expression, where we have S2O8 2 minus plus 3I minus giving us 2SO4 2 minus plus I3 minus. Okay, remember that when we write a rate law, we write it in terms of the reactants. So we're going to do rate equals K times the concentration of S2O8 2 minus to the X power times I minus to the Y power. Okay? In this case, we have two reactants, so we have to make sure that both of them are present in our particular rate law. All right? So we can kind of look at these, and if we look at our experimental data here, when we go for experiment 2 and 3, we're going to keep the concentration of the S2O8 2 minus constant. And if we look at 1 and 2, we keep the concentration of the I minus constant. Okay, that is, we did this on purpose. It's designed that way because we can say that to find the order with respect to S2O8 2 minus, the I minus must be held constant. Okay, and the concentration of S2O8 2 minus must change. So from this comment right here, we can say to determine X, use experiment 1 and 2. Okay, because in experiment 1 and 2, the concentration of our S2O8 2 minus is changing and the I minus is staying the same. So if we take experiment 2 over experiment 1, just like we did in our last example, we have the concentration of S2O8 2 minus, which would be 0.045 divided by 0.15, that's to the X power, times 0.21 divided by 0.21 to the Y power. Okay, this is going to equal the rates, which are going to be 3.41 molar per second divided by 1.14 molar per second. All right. As you can see, this term right here, 0.21 divided by 0.21 is going to be 1. So 1 to the Y power is going to be 1. So we can ignore this term right here because anything times 1 is going to be itself. So here we have 0.45 divided by 0.15, which is going to be 3. So 3 to the X power is going to equal 3.41 divided by 1.14, and that's also going to be 3. If we take the natural log of both sides, we can bring this X down in front. So X times the natural log of 3 equals the natural log of 3, and here X is going to equal 1. Okay, so this reaction is first order with respect to the S2O8 2 minus. Now we have to go back and do the same thing to try to figure out what Y is, which is the order with respect to I minus. And for this, we need to keep the concentration of S2O8 2 minus constant and change the concentration of the I minus. So to find Y, we're going to use experiment 2 and experiment 3. So to show this, if we look at our experimental data right here, in experiment 2 and 3, the concentration of S2O8 2 minus is 0.45 in each case. So that's going to be raised to the X power times 0.21 divided by 0.12 to the y power. That's going to equal 3.41 molar per second divided by 1.95 molar per second. Again, we have 0.45 over 0.45, so this term right here is going to be 1, which we can then ignore. We have 0.21 divided by 0.12. That's going to give us 1.75 to the y power is going to equal 3.41 divided by 1.95. That's also 1.75. So that means y times the ln of 1.75 is going to be equal to the ln of 1.75. So y is also equal to 1. So now we have to write the overall rate law, which would be consistent with what we have written at the top here. So the rate is going to equal K times the concentration of S2O8 to the first power times I minus also to the first power. We can now use either one of the three experimental data that we have right here to determine K. So I'll just plug in the first one. 1.14 molar per second is going to equal K times the concentration of S2O8 to the first power, which is 0.15 molar, times 0.21 molar also to the first power. If we rearrange these, we get K is equal to 1.14 molar per second divided by 0.15 molar times 0.21 molar. So one of the concentrations here is going to cancel out, and K is going to be equal to 36.2 molar to the minus 1 seconds to the minus 1. Okay? And we can take this to write the overall rate law, which is going to be rate is equal to K, which is 36.2 molar to the minus 1 second to the minus 1 times S2O8 to the first power times I minus also to the first power. And this is our overall rate law for this particular expression. So to kind of recap what we've done here, we can look at, in order to determine a rate law, we need to look into experimental data. So here we're given experimental data. We've designed this experiment, so in one case, we keep the iodide concentration constant and vary the S2O8 concentration. In another experiment, we keep the S2O8 concentration constant and vary the I minus concentration. This is going to have an impact on the particular rates. Notice that when we triple the concentration of S2O8 from experiment 1 to experiment 2, the rate triples. Okay, so that kind of tells us, that this will be first order with respect to the S2O8. Okay, we can do the same thing for the iodide, and we go through, we can figure out, the first step is to figure out the order of each of the reactants. In this case, there's 2 reactants. Sometimes we'll have 3, so we'll have to do this thing 3 times, right? So we can determine that. Then we can go and determine what the rate constant, K, is by looking at any one of the 3 experiments, trials in the experiment. And here I just picked the first one. We get 36.2. So our overall rate law is 36.2 molar to the minus 1 second to the minus 1 times the concentration of S2O8 to the first power times I minus to the first power, which is written down here inside this red box.